we go. Okay. All right. So let me. The speaker. There is some echo. Maybe it's here.
I know my. Mute the laptop.
Yeah. Is it right? Okay, so welcome everyone for the first seminar of our IAIFI seminars, and to start this season in like with something that we are not familiar with, we go all the way to AI and mathematics. So we have today here François Charton from Meta AI that is going to talk about one of his last topics of research, that is discovering global Lyapunov functions. So please, I'll leave you the floor.
Thank you very much. So I'm going to present, I have a work in physics with Lance Dixon, but you heard of it because two of the postdocs there were in the seminar recently and talked about it. So I thought I would talk about something else. So this is about a recent paper. The paper will be on arXiv next week or week after next, but it's just fresh. And it's about discovering Lyapunov function. And in my opinion, it's one of the first time, so far, when we do AI and math, we've mostly been working on math that we already know how to solve. Even when you talk about the IMO are not open problem. They're difficult problem for extremely gifted teenager, but nothing is open there. Same when we do arithmetic or other things like that. There's a few things by DeepMind that are close to open, fun search, the thing they discovered on combinatorics is sort of new. But this is really an open problem, and long-standing open problem. And well, you'll see if we can say we have solved it. But the subtitle is important. What I wanted to insist on it, what it takes if we want to push AI to the next step, which is, collaborating, actually being an assistant to mathematicians and physicists to help them propose candidate solution to very hard or open problems. Okay, good. So I'm going to talk about dynamical systems. So a dynamical system, it's a system of n equation in n variable, such that you have a function that defines the gradient everywhere. So you got a function x dot equals f of x, okay, where x is a point in Rn, the phase space, and f is a function from Rn into Rn. So there's a basic theory on stability, which says that if you want to have an equilibrium, then you need f to be equal at zero. In some point in x0, the gradient needs to be zero. And the theory says that the system is locally stable. So you have a stable equilibrium at the point if you calculate the Jacobian of f, so the matrix of all partial derivatives, and you take the eigenvalues, which are complex because it's an n-square matrix, not symmetric, nothing. And if all those complex eigenvalues have negative real parts, then you have a stable equilibrium. This is known as the spectral mapping theorem, and it's something that you can do. So a couple of years ago with Amaury Ayat and Guillaume Lampe, Amaury being a co-author on the current paper, we showed that you can train a transformer to do that. This, again, is a solved problem, but we showed that this was possible. You can input into a language model the system and get the stability and actually the value of the real parts of the largest eigenvalue. But the problem I'm interested here is different. It's the global stability of the dynamical system. So suppose you have a stable equilibrium at x0, which I will take to be the origin. Suppose now you have a trajectory that starts close to zero, close to the origin. Can I guarantee that at all time, I never get out and I get very far from there? So if I start in the blue ball, do I stay in the blue ball or in the red ball or something? So do I have this kind of stability? And you see it's a much stronger requirement than the requirement of local stability. So it's a very, very famous problem that has been studied by very famous people. And it was studied notably. So the n-body problem is not exactly the same thing because it's a slightly different, it's a very related problem, not exactly the same, but it was studied notably by Poincaré. And it was sort of made famous recently by Netflix. I think that's the first time you see a slide with Netflix and Poincaré on the same slide. And actually, we have a solution. We have a theoretical solution of this problem, which was a very surprising one and an old one, which is due to Lyapunov. So in 1992, so not very long, well, the time of Poincaré, basically. Lyapunov showed that if you can find a function V that is C1, so a function, a C1 mapping from Rn, the phase space, onto R, such that for every X, V has a minimum at 0, and it's a strict minimum. V is infinite at infinity. And you have this dot product of the gradient of V dot X, which is always negative. Then the system is globally stable. And if you start close to the origin, you end close to the origin. Yep. Yeah, continuous differentiable. So the thing here is that you have this property, which, so you can think of V like some kind of entropy that would go decreasing along your curves or something like that. It's a function that, so every time you're on a trajectory, it moves and it goes down towards 0. And this is what guarantees the thing. So this was a very surprising result. It's a sufficient condition, but throughout the 20th century, many mathematicians proved that for a very, very large class of system, it's also necessary. So it's a sufficient condition, but it's almost necessary, if you like. I will talk about another thing here, but just to mention, you have three conditions here. You see V strict minimum, infinite, and the dot product. You can relax the strict minimum condition, Vx larger than V0. If you relax it so that it's not strict anymore, you have something called the barrier Lyapunov function, which is, you can think of it as a non-bounded equivalent. In that case, V defines two subspaces. V equals 0 defines several subspaces. And you never leave, if this happens, the curves never leave the subspace you start in. So there are areas in the phase space, and you never leave them if you have this. So that's a weaker problem, and we'll see it at the end of the talk. To give you an example, so this is an actual function that our model could solve. It's a very stupid system, I agree, but it's simple to explain. So you got a system that is x0 dot equals 2x1 square, x1 dot equals minus 10x square. V, a correct Lyapunov function, there are many, of course, is this one. So you can see that it's a polynomial in X, so it will have a strict minimum in 0. And you can calculate the gradient, and notice that the gradient is the dot product of the gradient, and F is always negative. So this system has a global equilibrium, a stable global equilibrium in 0. Yeah. And there are others, so I show polynomials, but of course not all of them. And it's sometimes funny because it was proven in 2011, I think. People thought that polynomial system would have polynomial Lyapunov function, and some people proved a couple of years ago that actually it wasn't the case. They exhibited a polynomial system which had a totally non-polynomial with a log Lyapunov function. So the funny thing about the problem is that the Lyapunov theorem is great, but it gives systematic way of finding V. It doesn't even give you a way to prove that the system is stable. The only way to prove a system is stable is to find a V, and you don't have a constructive way to find it. So right now, the state of the art is that there's no systematic method. So people have a bag of tricks that they know might work, a bit like when you do integration, you have tricks and you try many of them. You can do your whole PhD thesis to discover one Lyapunov function. You can have a PhD for that in mathematics. There exists numerical methods in very special cases. So when you have a small number of variables, F is a polynomial of low degree, and V is a sum of square of monomials, then you have a numerical method, which is, there are tools for that, called source tools, same sum of square tools. But these exist, they are very computationally intensive, and unfortunately, they don't even cover all the polynomial systems, since we know there are stable polynomial systems that have no source Lyapunov function. A couple of years ago, some people introduced neural networks for this. So they introduced neural network for a weaker problem, which happens to be very important, notably in robotics. Sometimes you want a system to be stable with respect to small perturbations. So you have a small equilibrium, you have a stable equilibrium, and you are going to change the system a little, but from very, very small. And in that case, if you have a good approximant of a Lyapunov or something that looks like a Lyapunov function, you can prove that your system will remain stable. So it's important, for instance, in robotics, where you're usually at an equilibrium, and every time you move, you want, the result of the movement to keep you in stable, to keep you with something stable. Okay? But the global case, the fact that you often want stability, not for small displacement, but for large ones, is very important. So think of epidemiology. You're absolutely not interested of knowing how the epidemics will come if one more person or two more person are ill. You're not interested in flood control to know what happens if it rains a little, or transportation. You are always interested about extreme case. So large deviation from the, usually large deviation from the equilibrium. Okay, so that was for the problem. So with Alberto Alfarano and Amaury Ayat, we were interested in treating this as an AI problem. So what we want to do basically is we want to take a transformer, a language model, and we want to train it to predict V, the Lyapunov function, from F. We want to do this, as usual, by presenting the model with tons of examples of V and F, so that the model is going to learn to translate F, which is a sequence in some language, a sentence in some language, into V, which is another sentence. We can write those functions, so they're basically sentences, right? And then we want to use the trained model to suggest possible V for a given F. So this might look like crazy, but a couple of years ago with Guillaume Lampe, we did symbolic integral this way, and we did pretty much as well as Mathematica. So if it works for integration, without any mathematics, just like translation, why not for Lyapunov functions? So let me recap what I want to do here. So I want to do 5 things. First, I need to generate a lot of training examples to train my language model, because everything it will have will be examples. Then I'm going to need to encode the F and the V, the system and the Lyapunov function, as sequences of words in a language, because transformers process sequences of words. Then I'm going to need to train a language model. And finally, when the model is trained, I'm going to need to generate for a given F a number of guesses of V, of the solution, and I'm not going to need to check them and hopefully find one. Okay, so let me talk about the 4 last points first. The hard part is the first point, of course, but let me talk about the next one rapidly. So that's the easy stuff. How do you encode F and V as sequences of words? Well, F is a system of symbolic functions. V is a symbolic function. You can always represent a function as a tree, abstract syntax tree, etc. This has become very standard. So you see cos 2.1 x0 times x1 plus 2. I can easily represent it as a tree here. Multiplication being got the product of this and that, and then the cos of this times that, etc. And once you have a tree, it's very easy because you can enumerate it. So typically in pre-order notation or Polish notation. So you start from the top, enumerate the parent before the child, left child before right child. So here, start from the top. So it's time, then left child cos times 2.1 x0 plus x1, 2, etc. This ordering is not really important. It could be in any kind of, so long you have something to enumerate a tree, you'll find. But practically, this shows that, okay, it's relatively easy to encode all this problem. There's nothing difficult in making sentences out of all that. Training a model, so we're using a transformer model. It's big from my perspective of AI for math. It's very small from LLM's perspective. We have 8 layers, 640 dimensions. I think we're around 100 million parameters. So we're very far from the billions and tens of billions and hundreds of billions from elsewhere. The model is trained to predict V given F, and it predicts it token by token, word by word. So you give F to the model, and it predicts V0. Yeah. So we'll see most of the training sets we use will be 1 million example, but we have one of 100,000. I used to say that you need tens of million, and I've revised this opinion over time. I noticed that, for instance, the thing we do with Lance, we manage with 200,000 examples. It works. So hundreds of thousands of examples, let's say, or more. So yeah, so you predict the first token, then you give the model F and the first token, and it predicts the second, etc. Predicts the next letter. How do you predict? How do you train a model? Well, you train the model, in pure language style. There's no mathematics involved. You minimize the cross entropy, so the probability of getting the correct the correct next token. So if the next token is the correct one compared to the solution you have in your test set, in your training set, then the model gets kind of a reward. Actually, it gets nothing. And if it's wrong, it gets a gradient back that modifies the weights. So you start with a model with random weights, random model parameters. You show batch of examples after batch of examples, and every time you calculate gradients, you move the weights and so on until hopefully it converges. What do we do when we have trained the model? We want to generate several guesses of these, so we use something called beam search. So, you know, models don't predict a token, they predict a distribution of probability for the next token. So instead of taking the most likely token, you take like the 5 most likely. So you got 5 first word for the next. You do that with the second, you got 25, you keep the 5 best, and you go on. So this way you can have as many guesses as you want, and it costs you very little. So it's a good thing, because it's always better to try to have many guesses for the problem. And then we are going to do math. This is actually the only place where we do math in this. We need to test the guesses. So all these methods are predicated on the fact that you have a verifier that you can check the results. So in that case, what you do, you have a sequence that represents V, you decode it into a function, and then you either use numerical methods or SMT solvers to prove that the Lyapunov condition holds. So to prove that V is positive and have a strict minimum in 0, to prove that V is infinite at infinity, and to prove that the gradient is negative. The thing is that the method we use don't always work. They work about between 85 and 90% of the time, which means when my model send me a V, a solution, the model will never have a false positive, because if the model says it's good, it's good. But it happens that the model cannot decide, that the tester, the verifier cannot decide, in which case usually the program will crash or will take, you know, a very, very long time. It's either works in 30 seconds or it never works, basically, for my experience. And so you have to remember that we have a verifier, so we may have false negative. So all the accuracies we report are underestimated, but there's nothing we can do about this. Okay, so now I'm back to the real stuff, which is generating pairs of V, F, and V. You know, I need hundreds of thousands, maybe 1 million examples to train my model. How do I get them? So in a perfect world, it would be very simple. We would generate a random stable system F. We would compute the Lyapunov function with the solver that we would have magically, and we would have the pair FV that we would add to the training set, rinse, repeat 1 million times, and we're happy. But wait, what? We cannot generate a stable system. We cannot even prove a system is stable. So if we generate a random system, most likely it won't be stable. So I can't do that. And how to compute the Lyapunov function? We only have solvers for the simplest case, and we don't want to train on the simplest case. We want to solve everything, right? So this doesn't work. So we're going to use, so this method we used to call it forward. You know, you generate the solution from the problem. So we're going to study another approach, which we introduced a couple of papers ago, which we call backward. Instead of finding the solution of a problem, you find the problem of a solution. So you generate a random solution, and then you try to find a problem. So you want to sample a function V, a possible Lyapunov function. And from this, you want to construct a system which has V as its Lyapunov function. So reminding you what I want for my Lyapunov function in my system, you see I have 3 conditions. The 2 first conditions are specific to V. So when I generate V, I want to generate a function which is infinite at infinity and has a strict minimum at 0. That's all I need. Once I have such a function, I want to find F, verifying the dot product relation. So the backward method, I want to select a random function, a C1 function, with a strict minimum in 0, infinite at infinity. Then I find a random system. But there are constraints. I want F and V to be as generic as possible. You know, very special or very particular solution won't do. I want to train a system on that. So I need to have the most variable, the most generic F and V possible. So ideally, I would like to sample V from the class of continuous node derivable functions with a strict minimum at 0 and infinite at infinity, any one of them with as little bias as I can. And for a given V, I would ideally be able to enumerate all the functions, you know, F, or have a way to sample among all the functions verifying my Lyapunov condition. So this is the first constraint. There is the second, much harder constraint, is that I want to train my model to solve the Lyapunov problem. I don't want to train my model to reverse my generating procedure because I'm using a trick to generate my f from v. Suppose I can reverse that, then I'm in trouble. I'm not solving the right problem. So giving you here a very trivial example that this won't happen, no one would do that. Suppose you want to calculate the roots of a polynomial with integer coefficient. You know, you want to attack Galois-Abel and you want to do better than them. So backward generation is also tempting. I mean, you get 3 roots, you multiply them and you get a polynomial. But of course, if you train the model by giving it p of x, you know, the factorized form, the model is not going to learn to solve the polynomial. It's going to learn to read 2, 5, and 7 inside your function because you put it there for it to see. So, of course, the solution is very easy. If you defactorize, if you develop the thing, then you give this and you want to find the roots and it becomes a hard problem again. But what I'm trying to say here is that the generation method can't very well leak information about the solution into the problem. And you have to be extremely prudent about that because you might be solving an easier instance of the problem or a different problem just because of the leakage. You know, it's a bit like data contamination, you know, when you have sort of the test set training example that make their way into the test set or similar things. Yeah, so naive method will not work. You need to find a way to sort of obfuscate the generation method. And there was a paper in 2020 by Yehuda et al. That shows that actually for hard problem, you will never be able to guarantee the absence of such leak. They made, you know, based on complexity theory, they made this point. So the best you can do is do all you can to avoid leakage, but you can never be sure there is none. So back at generating V, I'll be a bit long on that so that you can see how it works. So I want V infinity with a strict minimum in 0. The problem is the strict minimum. It's a hard problem to generate any random continuous function with a strict minimum in 0. There's no simple method. So the way we do it, which others have done before us on this, is that you split V as V proper, V cross, where V proper has a strict minimum but is from a smaller family. And V cross is just non-negative unbounded and changes nothing to the problem. And you can take it into a very large family. So for V proper, but it seems very logical. You know, you're going to take the entries of random positive definitive matrices, build a positive polynomial out of it. That seems relatively straightforward. You don't need V to be a polynomial, so you can modify it by any generic increasing function. It will keep the small minimum property, right? So this is easy. You could multiply by any random positive function. So you want to add a lot of random stuff into V so that the V is never belongs to a small class on it is, you know, easy to find because it belongs here to a small group, just polynomials and all that. And V cross is just a sum of square of bounded functions. So you generate something like this. And with this, you have a fairly good approximation to a very generic potential Lyapunov function. And this verifies the 2 conditions you want, right? So next step is generating f from V. So what we want, it's only one condition now. It's easy. I want nabla V, the gradient of V, dot f to be always negative. So there's an obvious solution. If I take f equals minus nabla V, it works, right? It always works. But of course, it's a bad one. I said naive method wouldn't work. Because if you do that, what you are doing is not solving the Lyapunov function. You're just integrating. The problem you have now is not finding V, the Lyapunov function, is finding V, the integral of f. And you know, it's not an easy problem, but it's not an open problem either, and it's much easier. So you cannot do that, but there's an easy way to modify that. Suppose you multiply all the coordinates of nabla V by your positive function, so an h square from a fairly large random function for a large class. You can see that the dot product will still be correct because you'll have the nabla V square appearing everywhere. But if you do that, integration will become impossible, okay? The only thing you have with that, so here you have a better solution, but it's not perfect because these functions verify nabla V, etc., but it's not completely generic. So you could improve it by adding a random vector W satisfying W dot nabla V equals 0. This doesn't change anything, but it makes the the family of f that we generate much, much, much larger. So we want to find a vector from the hyperplane, the normal hyperplane to V, the hyperplane orthogonal to the gradient. So you can generate that by generating a random base of V and having random function, and there you go. But again, and I promise I'm finished after that, but I want to, yeah. With do the W. Well, the thing is that in order to generate the W, you need to know h of x. So you need to have a base of the hyperplane. So the idea is that you need to generate the hyperplane. These are functions. So you need to calculate EI of x, so a base for every direction perpendicular to the nabla, right? So the funny thing, that's my last comment on that, is that you have to do that, but you have, again, not to be naive. You want to generate a base of an hyperplane, you're very tempted to use Gram-Schmidt. Don't. If you use Gram-Schmidt, then you see the denominators of the form, it will be normalized. You want an orthonormal base. So the norm of nabla V is going to appear in the formula. And it's leakage. I mean, you won't recognize, you won't reconstitute V from the norm of nabla V, but it helps. Normally, it will not simplify. Usually, things never simplified in those kind of space. So you go for a non-orthonormal base. You make the EI of x, so the base, as simple as you can. And there you generate random functions. So, yeah. So summarizing, we generate a function f, which is a sum of two elements, a proper strict minimum function and a function which is non-zero. We generate a system which has this form that verifies the Lyapunov function. So these are correct examples. These are examples of f and v that are guaranteed to have a Lyapunov function. The good thing of this method is that it depends on a number of random functions. So it's a simple set of operational random functions. So we can constrain those functions to belong to different families. So we can generate different kind of problems, polynomial systems, non-polynomial systems, polynomial Lyapunov function, sum of square Lyapunov function, anything. It's good because we will want to compare ourselves to polynomial systems, which are the only baseline we have. Lots of steps. That was the point I was trying to get across. I hope you got it. Lots of steps were taken to ensure that the generative procedure doesn't leak information, but we have no guarantee. So the only thing we can say is we really did our best try at that. So after all that, we generate two backward data sets of 1 million example, a backward data set of polynomial system of 2 to 5 equation and 2 to 5 unknowns, okay, in order to compare to the current state of the art, which is only polynomial, and a backward data set of non-polynomial. So actually the non-polynomial we create here for practical reason are polynomials where the monomials are functions of more complicated functions. So like trigonometric polynomials or polynomial where terms could be exponentials or logs or trigonometrics or function of this type. Okay, and we generate two, since we have source tools, we generate two forward sets, one on Lyapunov problem. So those sets are smaller because it takes a lot of time. We had to parallelize it on thousands of CPU to get this done in a couple of weeks. So 100,000 polynomial system that source tools can solve. And since the barrier Lyapunov function is easier, we tried the barrier Lyapunov function. So we have 300,000 system for which source tool can find a barrier Lyapunov. So that's the case where V of x is not strict, doesn't have a strict minimum, but a minimum in 0. Okay, and it's the case where everything is non-bounded. So that's kind of a related problem, if you like. So first thing we did was measure, in-domain performance. So you train on a set, you sample like 20,000 or 10,000 examples from your train set that you keep away, you don't see them at training, and it serves to evaluate. So the first interesting thing you can see here, so this is batch size 150, so one guess, 50 guesses. For the forward data set, you can see that my model trained on barrier function or trained on Lyapunov function. So my model trained on barrier function achieves 93 or 98% accuracy on source tool functions. Okay, so that's good news. It shows that, on the things we have on the polynomial system, our models are learning. And same for the Lyapunov function, we go up to 90%. For the backward models, it seems very good, but this is very deceptive. I mean, because if the model have been exploiting a gap, leaking information, or solving another problem, I would observe exactly this. So the first lesson you have here is that when you're in this situation of solving, an open problem with a backward method or any method that generates problem from solution, in-domain performance are worth nothing. You cannot say anything about it because your test set comes from the same generator as your data set, and so it has the exact same flows. Okay, if there is a flow, it will appear here, and you will not be able to see it. So what I'm saying is that the only way to test those models is for out-of-domain performance. So you train on backward, you test on forward. You train on forward, you test on backward. Because in that case, there's no leakage possible because they are not generated with the same method. So you can see here, if you train the backward data sets, B poly or B non-poly, and test it on FLYAP, so on the same global Lyapunov function, but generated on polynomial that source tool can solve, you achieve 75% accuracy, which is not bad. So this shows that, yeah, maybe the model is exploiting some leakage, but not absolutely, because it still learns something. It still learns to do Lyapunov function. If you go on a related task, it's less good, but I was sort of surprised. This is sort of zero-shot learning. You are able, with this model trained on the global function, to learn a related problem, which is a barrier function. And this was nice to see. If you look at the forward data set, on the other hand, it's pretty catastrophic. And this shows the limitation of source tool. This shows that, I said not all polynomials can be calculated. Actually, if you generate, not random, but special polynomial, like the one we generated backwards, the performance of those models is actually very bad. Okay. So the thing here is that it's a nice result because we're saying, okay, we are able to learn to predict Lyapunov functions from backward generated data set and test it on forward generated data set, and probably there is no leakage or exploitation. The model cannot cheat on those. The problem, there's a cost to that, which is out of domain. The only way to test my model is that I have to be out of distribution because the backward distribution has no reason to be close to the forward distribution of problems. So the penalty I have to pay is the 75%. It's not as good as it could or as it should. So can you do better? So a year ago with Sami Gelassi, we had a paper on priming, on something we call priming. So the thing is that OOD generalization is hard, and we were studying something a bit special, which was what we call length generalization. When you train a machine to add numbers, and you add numbers with 10 digits. Usually the model trained on 10 digits doesn't generalize to 20-digit numbers. And that's length generalization. But we noticed that if you add a tiny number means a dozen or 100 in a million examples, of longer examples, so numbers with 20 digits, everything went fine. So priming meant that you can do a lot against out-of-distribution generalization by just providing a few examples of the distribution you want. And here we're in luck. The distribution we want is the source tool distribution, and we have a few examples. So of course, we won't take them from the test set. We will generate new examples. But that's what we did. So here I'm taking my B poly, so my polynomial backward training set, and I'm taking a small number, a few hundreds, well, a few tens or hundreds or thousands of examples from either F-bar or FLYAP, so from the forward generated data. So I remove those guys from the test distribution so as to have no contamination, but you see the idea. And you can see the performance. If you take only 100 examples from FLYAP, your performance goes from 75 to 82%. I'm talking of 100 examples out of 1 million training data. So it's, it's a tenth of a thousandth of a person. So a tenth of a thousandth of the set. So it's really, really small, but you get a lot of performance. Even better, if you train on F-bar, you put on it 300, you get improvement on both tasks. So that's, if you want, that's few-shot learning. So it's very interesting because it's a very generic technique. You have this hard problem that you cannot solve, so you need to do the backward method. But if you have a few examples of a distribution close to the test distribution, please use those. So take them from a textbook, from anywhere, because they are going to help and to really help. Okay, so we compared to the state of the art, this is classic. So this is what we have with the training method, with the mixture. So polymixture is the backward set plus the few addition. So between 84 and 99%. You can see source tools. So source tools on F source tool F bar is 100% because by definition we build them from source tools. So there's no way to compare. But you can see on BPOL it was only 15. And you can see the previous AI method are not, they're not ridiculous. They're not at 0, but they're way lower. In their defense, we must say that they were absolutely not built for this. So it's also not very surprising that they don't succeed. So we can say we're at state of the art. So where are we? What have we learned so far? So I've shown that model trained on backward dataset can generalize to generic polynomial system, the system that source tool can solve. I've shown that priming helps and allows generalization to do, and we do better than existing AI method. So we've sort of won. But wait, I said I would work on an open problem, and it's not an open problem. The source tool can solve our problem we know how to solve. So we're only solving polynomial systems that are already known to be stable. So in French, we say tout ça pour ça, all this for this. So that's a bit disappointing, but we can try. So now we go into the wild. So the idea is that you could generate random systems. So that's what we're going to do. We're going to generate free test set of random systems with a guaranteed local minimum. So, we're going to calculate the Jacobian and look at the eigenvalues. But those systems are not guaranteed to be stable. We have absolutely no guarantee, so we expect low performance because many of those have no Lyapunov function. But those systems come from no model and no one knows how to solve them. They're just random systems. So I got a system of small polynomials, degree 2 and 3, polynomials of degree 2 and 5, and non-polynomial system generated with the same kind of system as the one I had in my training sets. We don't expect very good performance, and what's most important, I don't know what the baseline is. I don't know the proportion of stable system there. It could be 10, it could be 20, it could be 60, I don't know. So on those 3 models, so you see you got about 60,000 polynomial system and only 20,000 non-polynomial. You find that source tool works very badly. We've seen that already, and it means that source tool works, source method works, but for very specific polynomial system, not all of them. You can see that the AI methods, so those 2 are just as bad as source tool. This one is a little better, and it's hard to know if it's really better because we don't know what's the actual value. But our models on that achieve 10%, 10, 11, 12%. And these are good because these are things that we don't know how to solve, and other methods are way behind. These are systems for which there is no known method. So what we are saying, we don't know how good this is, but we said that the backward prime model achieved 10 to 12% accuracy on random system, even non-polynomial system. So I think this is very encouraging. I don't know exactly if we've really solved the problem, but we are getting close to, to solving open problems. We can, of course, prime, the system that we applied can be reapplied as the magic of priming. I can use wild examples, do my model on it, see the one that the model predicts correctly, add them to the training sample, retrain the model and retry. And I can bootstrap this way. If I do that with 1,000 examples, you get a small improvement. It's not huge, and at one moment you will end up with model collapse, that's for sure, but you can grab a few % of performance out of that. So you can see the model does pretty well. It solved 10%. So at one moment, it was funny to know, and how do humans work? So it happens that Amaury, my co-author, is a professor at École des Ponts in France, and he teaches Lyapunov function. So we took 75 of the polynomial function and turned them into an exam. So those were first-year master students after a semester learning Lyapunov function. So we were not cheating. Everyone had 3 systems chosen at random, and they had 30 minutes. And we got an average performance on the master student of 9.33%. which is significantly lower than a model. So maybe by having longer timeout periods and more students and better people, we would get better. But this still gives an idea that, you know, it's not a trivial problem, and we're not just comparing two machines. So this is my last slide. So what have we done? We managed to solve, you know, random problems in the wild. We managed to solve random problems that no one know how to solve. So we're close to solving an open problem. I would say we're not there yet, because what we want to solve is not a random problem. We don't care about random system. We care about interesting system. Interesting system is interesting dynamical system that dynamical specialists would have. So the next step would be to, you know, to find interesting system that sort of fit our bill and see what it happens. And we'll definitely do that. I'd like to finish on three, you know, wonders, or three things I'm curious about that. So the first thing, I said it again, and it's very, very important. Generation is really the hard part. If you work on an open problem, your real problem is how to generate your data. And backward generation is a technique that works in many cases, but it's absolutely not systematic. I mean, we spent 5 years on this project. We started this project during COVID with Amaury. And it took so long because every time we got a good result, we second guesses ourselves and we say, no, the model cheats. So that's how we came up with a crazy backward generation method, because it was impossible to, you know how to do it. So we need better systematic methods. I've been talking a lot of out of distribution. You know, I've said backward distribution, backward technique is out of distribution by design. This is absolutely badly ill-defined. You know, what is the distribution of problems? We don't even have a theory on that. We don't have a measure on the space of problem, etc. And this would be extremely important. So this is a real area of future research, especially for mathematicians or physicists, probably. What does it mean, a distribution? What does it mean to be far, to have a different definition on problems? Finally, we see those priming and bootstrapping thing, and I think this is an interesting takeaway and something that is definitely worth studying. That's all I have to say. Thank you.
Okay, thanks again, François, for the wonderful talk. Do we have questions? Jesse already have one.
Thanks, François. I'm fascinated by this issue of leakage, but I'm going to ask an adjacent question to that, which is that you have these functions and they're redundantly encoded.
Yeah.
That is, even if you have this tree, you know, you
Yeah.
can permute
Yeah.
elements of the tree, or you can put parentheses in different places, with like your example of a factorization.
Yeah.
So to what extent did you study or think about that redundancy and trying to find canonical forms for
Yeah.
functions so that leakage almost by construction couldn't happen, because it always gets set in the same form?
So the leakage I talk about is not this one. You know, the leakage at generation is something different, because it has something to do with the fact that I use an algorithm to generate my problem from solution. And this algorithm only explore a limited classes of problems and solution. And maybe the class I'm exploring is much simpler than the problem I want to solve. But in the case of the duplication, actually not in this paper, but in previous paper we had, so the first time we had this paper, you know, with Guillaume Lampe, we did the integration. Most of the training time of the machine was simplifying the system, because we wanted to have only one system. So it went through SymPy, and SymPy is full of bugs. So we had to do the things and we wait, and it would. The problem with that is that when you generate 1 million function, you cannot have a system that fails one time in 1,000, because you're going nowhere. So it's very complicated. So a few papers later, in the symbolic regression paper with Stéphane Dascoli, we actually said, okay, what if we don't simplify? And we had almost the same result. It's a little less good if you don't simplify the function, so push the model. So I only have a theory about that, but the way I see it is that when you don't simplify the function, it means that the relation between the mathematical object, the functions you have, and their representation as sequence is a one-to-n function. If the n is roughly constant over all the functions in the class, basically if you have 1,000 more and it's always pretty much 1,000 more, the impact of that is that you add something to the entropy of the sequence. But you don't care about the entropy. If this is constant, you only care about the gradient when you train. So you will have a slightly harder time training because you have more examples, and the machine will be a little more confused and you might end up a little lower. But I think, you know, with this hypothesis that it's that the explosion factor of the mathematical object to sequence is more or less constant, I suspect it has not a very large impact, and actually have observed it in case. I saw that for graphs, for instance. If you have a model training graph, a way to represent a graph is that you put a number of vertices and then you put the beginning vertices and vertices of every edge. So if your graph is undirected, you can swap everything and you can permute everything. Yeah, sometimes you can sort them, sometimes you don't sort them, and it doesn't matter. You run the exact same problems. In the case of graph, it's relatively easy because it's really one to n. The explosion factor is very constant. But here, I don't know. But my feeling is that it's not as bad as it looks.
Thank you.
Yeah, I had another question following along the lines of leakage. And has there been sort of an exploration of using different backward generation methods for test data sets? And it's sort of in the idea that there may be a different method of leakage that is like not known.
So yeah, that was our original method for integration with Guillaume. We had, the backward method in that case. Forward method, you have a random function, you calculate the integral. This is hard and costly. Backward method, you have a random function, you calculate the derivative. This is cool and nice and easy and fast and everything. But we noticed that the backward things, if you generate backward, you have small problem with long solutions. Forward, short problem, short solution, long problem, or the other way around. But you see, you have a difference. So we tried to do that with integration by part. Integration by part, you can use integration by part. If you already know f prime g, you get g prime f for free or something like that. So we had two backward methods that we mixed, and we observed the better results. So yes, this is the way to go. The problem is that, as you've seen, a backward method is fairly difficult to organize. So you might end up with the ID for one, but it's not a given that you might have an ID for 2 or 3 or 4. Where I would agree with you is, suppose you worked on problems that are mathematically better understood than Lyapunov functions, say graphs. You have lots of different possible representation or tokenization of graphs. So you could have different ways to generate your graphs, and a mixture would be certainly a good idea.
Hi, thank you for your talk. I'm interested in this idea of priming. So do you have rough numbers for like how many hard examples do you need to add to your data set for it to make progress on those hard problems?
So what you saw here was that it's very, very small. So here I'm adding to 1 million, and you see at 300, you get a lot of the progress already done. It gets better if you have 3,000 or 30,000. Here it's only 100, and you already get something. So the idea, what we had noticed in the paper with Sami, it was about the same. It was about 0.1% or something like that. That's why we called it priming, because it's very, very small quantities. I'm absolutely certain that this is problem specific. The proportion must be problem specific. And there may be distribution of priming that work better than others, but it's it has to be less than 1% or something like that for it to be viable. Else, you're talking mixture, and you need to have different models, etc.
Yeah, I just want to quickly follow up. The reason I'm asking is that I guess in science, it's often the case that it's hard to generate a big data set for high quality data, but then you can generate a lot of crappy, low resolution data very cheaply, right? So I'm wondering if you can have a large data set of crappy data, a small data set of good data.
Okay, I'm no physicist, so I won't embark too much in this, but I think, a typical application of that is HEP, high energy physics, because you have the generators, and people can use generator as much as they want, but every time they use a generator, even precise, they say, okay, it's slow, but it's generated, and there are things, so we're not on the right distribution. Priming should work in that case, generator plus a little bit of experimental data, the one the sun will let you have or something like that. And this should be good. So the same exists. So I'm not absolutely sure about, bad quality and high quality data, because if it's easy to generate data with, say, 4 significant digits, but the data you really want is 6 significant digits, I really suspect you're not working on the same problem, and probably priming won't help. This is only guesswork. I have, it would need to be tested, but I have the impression that priming only works when it's really the same problem. The way I tend to think about priming is, it's like a syntax problem. So basically, you've studied a certain scale of problem. You want to work to a larger scale. In that case, it was the length of the sequence. Basically, the model has learned addition. It knows. The only thing it doesn't know is that it hasn't seen a long number. But once you see a few long numbers, that's all you need to get everything right. But it's because it's the same problem. If you hope to learn addition and then prime to do multiplication, I'm ready to bet it wouldn't work. Or you know addition modulo something, and you want to try a new modulus, it won't work. That's for sure.
Thank you.
Any more questions?
I have a question. Taking a question from someone. So my question is: have you tried to do some interpretability on the trained models to see what's the underlying algorithm?
So on this one, no. On this one, no. So understanding the weights and all that, the models are way too complicated for that. So the only way you could do interpretability would be if you had a one-layer model or something, like the things that Nilanda does. You could do that, but here the models are too complicated. We did try to have a look at the failure cases to see, which were the things that the model couldn't do. At this point, I defer to the mathematicians because I don't understand the theory at all. What I understood is that the problem is sort of too difficult for people to be able to classify the errors. So whereas in many easy problems of mathematics, you usually have a fairly good classification and you can say, oh, it fails in that case, and I know it from a theoretical reason. Here, it turns out that you have not enough information about Lyapunov function and the function, you only have the Lyapunov theorem, basically, to be able to interpret the errors. So what I understood from what the mathematicians told me was that, yeah, you see patterns, but you don't know what they are.
So I guess in the spirit of that question also, when you applied it to problems in the wild, did you see much correlation between the problems that your method could solve and that the previous methods could solve? Like if you ensembled, would you do better?
I don't think we looked at that, but this is a very good idea. I don't think we looked at it. The problem you would have here is that the distribution of backward problem is very, very strange because you generate them from the Lyapunov function. So we could compare the Lyapunov function on the other hand and say, is the model always predicting the same Lyapunov function? In which case the model would just try the Lyapunov function or a family of Lyapunov function it knows and get lucky from time to time. I would expect the performance would be lower if it were just that, but maybe this helps. But this is a good suggestion. Yeah, we definitely need to try that.
All right. Is there any other question or on the Zoom? If not, I think we can thanks again, François, for the wonderful talk and inspiring conversation.
Thank you very much.
And yeah. Yeah, and as usual, we continue our conversation upstairs in the penthouse. So feel free to ask more questions. François is going to be with us for the rest of the afternoon.